in order to show this recursion formula, we're going to write the Young operator out in birdtracks. And I've done this here already, but let's slowly go through what I drew here. So this Young operator, it contains a bunch of symmetrizers, which we have here, and a bunch of anti-symmetrizers here. And I want to display only the last symmetrizer, the last anti-symmetrizer. With that I mean the symmetrizer and the anti-symmetrizer to which the last line connects. Each line connects to a symmetrizer and to an anti-symmetrizer. If you recall how we draw these diagrams. For each box there is a line. The kth line is for a box with a number k, and then this connects for each row. There is a symmetrizer, for each column there is an anti-symmetrizer, and then the line of this box connects to these symmetrizers and anti-symmetrizers. Okay, and we only show the symmetrizer here for which connects to the last line. Each of these anti-symmetrizers comes with a normalization factor, factorial of the length, the number of lines it covers, and that's why we have these additional factors here in order to compensate for that. So the lambdas here are the row and length, and the mu's are the column length for the for the symmetrizers and anti-symmetrizers. And then we have the product of the hook length here in the denominator. Okay, in order to calculate the trace, we have to connect the lines. Last line to the last line, first line on the left to the first line on the right, and so on and so on. So this would be the trace of this Young operator. And there's one more thing I should say. So these here, they look as if they had the same length, but of course it depends on the length of the column and the length of the row in which the box with the highest number sits, what the length of these symmetrizers and anti-symmetrizers is. So here in total, no, hang on, there's one more line. In total here we have n lines, because we have n boxes. And then let's say we have p lines here for the symmetrizer and q lines for the anti-symmetrizer. So that's the length of the row and the column of the box with the highest number. Now in the first step I don't want to connect all lines, I don't want to calculate the full trace, I only want to connect the last line on the left to the last line on the right. So we want to calculate what this expression here looks like. And we learned something cool in session 2, and that's these recursion relations here for the symmetrizers and the anti-symmetrizers. So we're going to use these. We're going to replace this symmetrizer here once by this and once by this, and the same for the anti-symmetrizer. And then we're going to see what we get. So there will be 4 terms now. Let's just copy this and put it here once more, and maybe create some space for some manipulations. So the first term looks like this. We just take off the last line from our symmetrizers and anti-symmetrizers, and this term comes with a 1 over p. Maybe I don't need the prefactor. Let's remove this. So this term comes with a 1 over p and a 1 over q. So that's this factor and this factor. And this loop down here gives us a factor of n. So we have n p over q, and then we are left with this diagram here. And what's this diagram? That's the diagrammatic part of the Young operator for the tableau with a box with the highest number removed. So that's already the diagrammatic part of the Young operator for t prime. Okay, let's do the same thing again. now we have to make other replacements. Ah, that was the wrong thing. I have to copy it again from up here. Sorry. So this one. So we want to put it here, make it a bit smaller. And this time I want to put these two symmetrizers with the lines crossed here and just the removed line here. So the same thing for the anti-symmetrizer, but for the symmetrizer we do this thing here. And that comes now with a p minus 1 over p times q prefactor from the recursion relations. Now look what happens down here. This line, the last line leaving this symmetrizer, makes this big loop here, and then it goes back into this symmetrizer. So we connect all the lines of these two symmetrizers, which means we can replace this symmetrizer with just one shorter symmetrizer. So we get the same diagram as before. So we get, but with a different prefactor, we get p minus 1 over p times q, and again the diagram which we need for t prime, for the smaller Young tableau. Okay, and now what happens when we do the same thing with the anti-symmetrizer? So we put one symmetrizer here and two anti-symmetrizers here. That's the third term. Then again we get such a loop, this time for the anti-symmetrizers, and we get back the same diagram once more. And that comes with a minus q minus 1 over q, because the recursion relation, oh, it's wrong here, the recursion relation. The recursion relation for the anti-symmetrizer has a minus sign here, which I wrote wrong in the first place. So it's this minus sign here, which I wrote correctly down there. So we get this, again with the same diagram. Okay, now there's the fourth term, where we have two such crossed lines in there, and this fourth term that actually vanishes. And we're going to look at this in a minute. So let's just ignore it for now and see what we got from the first three terms. We got the same diagram all the time, but with different prefactors. So there was an n, the denominator is always the same, an n, a p minus 1, and a minus q minus 1, so the ones go away, so we get n plus p minus q. So we get this, n plus p minus q over pq times this diagram here. And what is it? Let's write down the left-hand side as well. Maybe we need some more space here. Sorry for this scrolling. Oops. Take this one from up here. That's what we've been calculating. And put it here. That's what we've calculated. But now I included the prefactors again, so I should also write them on the right-hand side. So we get the product over the lambdas, the row length, the product over the column length, and the product over the hook length. Now, here we found the diagram, the birdtrack diagram corresponding to the Young diagram with one box removed, the box with the highest number. So what about the prefactors? When we remove one box, then one column and one row are just by one shorter. And these factors here, these factors p and q, they just cancel out one term from one of the factorials up here. So the pink part together gives the correct factorial prefactor for the t prime. And then we would like to have the t prime factor here for the hook length. So we just write like this. write it like this. That's the same. So we take this here, and now all the pink stuff together, that's really just the Young operator for the Young tableau T prime. So we got n plus p minus q, the hook length for T prime, the hook length for T, and the Young operator for T prime. And now if we really take the full trace, we connect all the lines over here, and we take the trace over here, then we got our formula. So what remains to be shown is that the fourth term vanishes.